All right, everyone, welcome to the stream. So today I want to be covering this new paper by a couple of folks at OpenAI that just came out. A lot of these authors are just like absolutely phenomenal. Let's go back in a sec. Um, so I follow pretty closely Nick and Chrysol's work, but also I was like very pleasantly surprised by Gabrielle and Chelsea. Like they have a very interesting Twitter account. So I thought like we could sort of go over this paper and some of the background to understand it, what this is really about. So just looking at the sales pitch that they have here. So they're saying we've discovered neurons in CLIP that respond to the same concept, whether presented literally, symbolically, or conceptually. And this may explain CLIP's accuracy in classifying surprising visual renditions of concepts and is also an important step towards understanding the associations and bias that CLIP and other similar models learn. Okay. So saying 15 years ago, Quiroga et al. Discovered that the human brain possesses multimodal neurons, and they respond to clusters of abstract concepts centered around a common high-level theme. It was the Halle Berry neuron, featured in both Scientific and American, that responds to photographs, sketches, and text, had a Halle Berry, but not other names. Okay, let's look at this. Oh, interesting. Okay, so this is not like just like computationally, it's not a computational response. It's actually it has a neuroscientific basis. So yeah, someone's neuron only responded to Halle Berry. That's interesting. And that's a higher level concept than you would expect. You would expect groups of neurons to encode concepts. Instead, it seems that like that's not true. So let's just keep going through this. So 2 months ago, OpenAI really announced the clip, and so I also have a clip right here. We'll go over it in a second. Um, and a clip is a general purpose vision system that matches the performance of a ResNet 50, which is the most common image architecture, but outperforms existing vision systems on some of the most challenging datasets. So each of these challenge datasets, ObjectNet, ImageNet Rendition, ImageNet Sketch, stress test the model's robustness to not recognize not just simple distortions or changes in lighting, but also to complete abstraction and reconstruction, sketches, cartoons, and even statues of objects. Okay, so it's just like a harder vision task than what we're traditionally used to. So our discovery of multimodal neurons in the clip gives us a clue as to why they may be a common mechanism of both synthetic and natural vision system abstraction. And we discover that the highest layers of clip organize images as a loose semantic collection of ideas, providing a simple explanation for both the model's versatility and the representation's compactness. Okay, so for example, like a biological neuron. Oh, interesting. So it doesn't matter how the concept is presented, like whether it's her in costume, whether it's a sketch, whether it's the word, like that causes a similar response. With the clip neuron, they're saying, okay, well, we can also respond to a photo of Spider-Man, a sketch, and the text. So these are all the same concept. Whereas here, for example, you have a human face, but it does not respond to text or anything else. So this is sort of the traditional Inception net. Inception net is really just like just a deep vision architecture. It's nothing uh, like the word inception comes from going deeper. It's not necessarily something related to anything fancier than that. So I think it should be helpful now, like now that we know why this work is impactful, because like now we have models that work over abstract concepts. I thought it'd be interesting to just go over Clip very quickly and then see what it's about. So Clip efficiently learns visual concepts from NLP, and it can be applied to any visual classification benchmark by providing the names of visual categories to be recognized. All right. So deep learning has revolutionized computer vision, labor intensive, costly. Okay. It is trained on a wide variety of images with a wide variety of natural language supervision that's abundantly available on the internet. And the network can be instructed in natural language to perform a great variety of classification benchmarks without directly optimizing for the performance benchmark's performance. Similar to the zero shot capabilities of GPT-2 and GPT-3. Okay, interesting. So it seems like it's a natural extension of the zero shot classifications of GPT. I have a video about GPT if that's interesting. Uh, but that's interesting. So really applying this sort of similar idea to images. Uh, okay, without using any of the original. Wait a minute. No, wait, this is it. By not directly optimizing for the benchmark, we show that it becomes much more representative. Our system closes this robustness gap by up to 75% while matching the performance of the original ResNet without using any of the original labeled examples. Okay, this is kind of crazy actually. Okay, how does this work? So I think it's like clip, large or something. What does VIT mean? We'll figure it out. All right, so first off, it seems like it beats ResNet 101, which is pretty big in of itself, 101 layers, right? ObjectNet checks a model's ability to recognize objects in many different poses and with many different backgrounds. Okay. Okay, so contrastive language image pre-training. Oh, interesting. So already the fact like this is very interesting in that I recently had a video about SimClear, which is also a contrastive approach to distinguish images. And it lets you build representations that are pretty good because if you can distinguish stuff, that means you can classify that they're different. So it's interesting. So it's interesting that this contrastive idea is becoming so relevant. And so contrastive language image pre-training. Okay, so we do something with language with this contrasting. Okay, let's see. Um, okay, Richard Socher and co-authors at Stanford developed a proof of concept by training a model on Sci-Fi 10 to make predictions in a word vector embedding space and showed this model could predict two unseen classes. The same year, they scaled this approach. Most inspirational is the work of Ang Lee and his co-authors at FAIR, using NLP to enable zero-shot transfer. Okay, okay. So far, so good. Okay, let's look at this image quickly. So we have a text encoder for a sentence, and then we have an image encoder for the image. That's cool. So we get two vectors out of these, and then from these vectors, looks like we place them. We put looks like we create all pairwise, like all pair possible pairs, and put it in a matrix. Okay, and then so this is the pre-training step, and then we create a data set classifier from label text. So plane, car, dog, bird, photo, text encoder, an image encoder, and then I see. So basically figure out like how to index into this representation. All right. So traditionally, this is interesting. They're saying like, let's say you want to get you have a pre-trained language model, and you want it to work on a new class of images. Well, either you train the thing from scratch on this larger data set, or you take the pre-trained model and fine-tune it on the new labels. So instead here, a photo of guacamole, a type of food, a photo of ceviche, a type of food, edamame. Yeah, it does kind of look like all of them. But television studio, podium, okay. There's a photo of a healthy lymph node tissue. It's got cool examples, actually very pretty. All right, so let's look at the key takeaways. So Clip learns from unfiltered, highly varied, and highly noisy data, and is intended to be used in a zero-shot manner. So we know that GPT-2 and 3 trained on such data can achieve compelling zero-shot performance, but they require significant training compute. And so now they're saying, how can we make this more efficient? Is adoption of a contrastive objective for connecting text with images. We originally explored an image-to-text approach similar to Vertex, but encountered difficulty scaling this. The contrastive objective using Clip is 4 to 10 times efficient. Was adoption of a vision transformer, which gave us a further 3x gain in compute efficiency over a standard ResNet. That's nuts. Like I wasn't aware that vision transformers were computationally more efficient than ResNet. I would have imagined that it would be a lot less efficient. Um, Bag of words, contrastive clip. Okay. Our best performing clip model trains on 256 GPUs for 2 weeks. Oh wow. Okay. Which is similar to large scale existing models. All right. Where's it? So it's flexible in general. So it learns a wide variety of visual concepts. So they measure clip zero shot performance on over 30 data sets. And learning OCR is an example of an exciting behavior that does not occur in standard ImageNet models. Okay. And this finding is also reflected in a standard representation learning evaluation using linear probes. The best clip model outperforms the best publicly available ImageNet model, the noisy student efficient net L2, uh, on 20 out of 26 different transfer data sets that we tried. Let's look at this. I wasn't aware ResNet is just like so poor actually relative to these other architectures. What is this? RN? Okay, so this is clip. Seems to be forward pass gigaflops per image. Okay, so okay, yes, so we need to compare this left to right. But essentially it looks like at least comparing it to standard ResNet, there's like about like a 7% improvement. And then it scales better with the compute, where it's like, well, with more flops, like this grows exponentially, whereas here, like, not so much. So it looks like Clip does well to count objects, but not so much at complex tasks like counting things. Uh, it also has poor generalizations to images not covered in its pre-training dataset. Okay, so it's the broader impact. So Clip allows people to design their own classifiers and removes the need for task-specific training data. The manner in which these classes are designed can heavily influence both the model performance and bias. So when given a set of labels, including fair face, race labels, and a handful of egregious terms such as criminal and animal, uh, this behavior drops. Okay. I mean, yeah, like I can imagine that a lot of these bias problems get like way more amplified. So let's see. We've tested whether a task agnostic pre-training on internet scale has inspired a recent breakthrough in NLP can also be leveraged to improve the performance of deep learning for other fields. And we're excited by the results, and Clip learns a wide variety of tasks. Okay, this is good. Let's quickly go over the paper. And is the okay, of course, also Alec Radford. And let's also just quickly skim the code. Okay, so let's get this thing here. Okay, so just gonna go to clip, and I'm just gonna just get some sense of how complicated this project is. Okay, so it looks like the actual project isn't that complicated. It's about like 600 lines of Python, and then the Jupyter notebook looks longer than that, mostly Markdown. So that's good. So it means like the idea is at the end of the day kind of simple. So okay, so how does this work? So we pre-process the data, image open clip NLP, unsqueeze it, and send it to the device because I guess it becomes an NumPy array. And then tokenize this sentence and also send it to the device. So now we have this image in text. We encode the image, we encode the text, and then we pass we pass both to the model. And after that, we do a softmax and we take the most likely entry. No, not the most likely entry. We just like, oh, sorry, we linearize it into a line, into a vector, send it back to the CPU so we can read it, and then back to NumPy. I don't think we need to do that. Oh, or maybe you do. I don't know. Um, long tensor content of given this can be used as the input to the model. Okay. So one thing I'm not too clear on is, are there pre-trained weights here? So first off, we're saying pre-process. Are we loading a model? So model is just encoding, and clip is just a straight tokenization. Oh, okay, we're loading a pre-trained model, which is VIT B32. All right, so let's just go to the source a bit. So clip, then clip. All right, so this is, I guess, where the model files are. And so when you're downloading it, you just like call the URL. I'm assuming you use like the request API to get everything. Okay, URL lib. It's the same idea. This is the image pre-processing stuff, like resizing the image, center cropping it. So this is like really nice. I really like these ideas in the and like PyTorch makes like a lot of this vision stuff very easy because it just you just compose the transforms that you want to do. A lot of these ideas I also cover in the SimClear tutorial. Okay, getting the list of models. This is loading the model. We download a model. You load it just in time. What else do you do? Okay, so tokenize here. How does this work exactly? So tokenizer, encoder. Does this pass in a tokenizer? From simple tokenizer, import simple tokenizers, tokenizers. What's simple tokenizer? Okay, so that's also here. Let's just take a quick look. Oh, it's actually a byte encoder and byte decoder. All right, so we have this vocab, BPE. Okay, this isn't like a yeah. Okay, so like that's interesting that they're actually looks like yeah they're turning it into byte tokens. So let's go to the model for a second, just to see how this all fits together. Um, so okay, so they're calling this a bottleneck, and this looks like a very traditional um, CNN architecture. So you typically notice there's a conv, a batch norm, some relus. Here there's only a relu at the very end, which is interesting because typically I'm used to seeing the relus interspersed. Um, and then what do they do? Okay, sequential ordered dict. Okay, and so I guess like they do like a bunch of them. This is the forward pass, which makes sense. They have this module called an attention pool. Okay, so this is, like you have the key, you have the projection, uh, and the value. So a lot of the similar ideas from regular transformers are here. So they're all linear layers. Transformers sound more complicated than they are. The actual implementation is often surprisingly simple. Um, so this is a different version of ResNet. That's fine. I think that's probably for their benchmarks and the layer norm, so that it works for FP16. Okay, but it doesn't look like it's using FP16. Org type, XD type. Oh, okay, never mind. It uses the type of this. Okay, that's all fine and good. Okay, so then we have the actual transformer here, and this transformer has some residual blocks, which is just you see this? So basically you create a sequential layer. So this is unpacked. So you're going to create a list where you have as many of these blocks as you have number of layers. And each of these blocks has a width, a number of heads, and an attention mask. And then you basically execute this whole thing sequentially. The vision transformer, I haven't looked at implementations of vision transformers before, but it looks like we have a class embedding, positional embedding, because I think the way vision transformers work is if you have, like, let's say an image, you would break it apart into parts, and then you need to keep track of, well, which part are you at? So that's where the positional embedding comes in. Because if you don't have it, then you just don't know the order. So and it seems like the order would probably be helpful. Okay, so the forward pass is a convolutional layer. Then they reshape it. Then they permute it. They concatenate the class embeddings with this. I don't know what this is really about. You can so the plus here is also concatenating the positional embedding. And then I don't know what ln3 is. What is this? ln3. Okay, so it's a layer normalization. Permute again. NLD, LND. Yeah, I actually like this convection. I wonder why these permutations here are so important. Like, I need to maybe read this original paper to figure this out. And then this is a matrix multiplication where you're multiplying x by the projection itself. Okay, finally, we're at the clip module now. So in the clip module, we have resolution, vision layer is a width, transformer heads. Okay. So if as instance vision layer is tuple list, like I don't know what this is about. Is there a forward pass? Okay, so this is the encode text part that we saw. It's interesting, like on these permutes, like I wonder why they're used so much. Yeah, this is the forward pass. So encode the image, encode the text, and normalize the features. It's all fine. Take the cosine similarity as logits. So I think this is like cosine similarity is used a lot whenever you see anything contrastive. So maybe this is where this is coming in. They do some weird stuff to convert everything to FP16. I'm surprised this stuff doesn't just work out of the box with PyTorch. So yeah, so they take the data, have it, because before having it's 32 bits. And then, okay, this is the whole model. And then they convert the weights of the model. How does convert weights work? Okay, so just making sure that this conversion is happening. Okay, this is fine. So I think what I'll take away from this, like, let's just go back here. Um, so we're gonna learn how to do a zero-shot classification. So we want to classify for image classes that we've never seen. And the way we encode these image classes we've never seen is we have an image encoder that basically takes some text. Like basically, you can use this. You can imagine like maybe the ImageNet labels themselves. You encode them, and then you take the image and you also encode it, and then you pass this to a vision transformer that needs to basically have some task that it needs to resolve. So this is the contrastive pre-training part. So this could literally be just predicting stuff from ImageNet. And then the zero shot part is, well, you have a new sentence that you create. You encode this new sentence, and then you can say, well, give me a photo of a dog, or like, let's say, given this dog, what's the text? So this is where this becomes interesting. Uh, but this is like, it's not exactly unsupervised in this case, like in the case of BERT, because you can use image pairs from existing labeled image data sets. But I guess the zero shot part is for new things, right? Like, so for images that you haven't, for image classes that you haven't observed in your dataset before. So I think here they also mention Clip in the DALL-E paper, right? So is able to create plausible images. Yeah. So Clip is mentioned what, like 4 times here. Okay, but it's not actually using Clip. So with DALL-E, for example, you may have also recently seen this, and it uses, I believe, a similar idea. Let's just go over the paper again. Okay, zero shot image generation. Okay, so learn the visual cookbook, learn the prior. Is there an architecture diagram for this thing? Oh yeah. So on this whole point on distributed training, like the next video I've been very excited about doing is going over the like how distributed training actually works in PyTorch. So I had a couple of videos on like model parallelism, data parallelism, pipeline parallelism, but I thought just like looking at some of the communication patterns, like specifically the all reduce and all gather libraries would be really interesting. So I should be doing that soon, probably this weekend, most likely. So let me know if that's interesting. Okay, mixed precision training. That's yeah. So everyone's doing mixed precision training nowadays. It's very useful. You don't lose out all that much. I still want an architecture diagram. I don't see it. That auto-regressively models the text and image tokens as a single stream of data. Oh, okay, sure. So I think what they're doing here is, so you remember you can mask text when you're doing stuff like BERT. So I should draw this out for you. Here, I'll do it on whiteboard. It'll be faster. So it's a sort of very similar idea. Like, whereas, like, remember, so in stuff like BERT, you're gonna have like these. So this is your sentence, right? And each part of the sentence, like this is a token, or let's say a word. And so what you do to learn in BERT in an unsupervised way is you essentially mask this. And then basically you pretend like you're not looking at it. And then given the surrounding context, like try to predict what this word is. Similarly, if you have an image, well, the image looks something like this, for example. Let's say this image, let's do a simple image for now. This is just like an image. So this is going to be 0, 0. Uh, this is 1, 0. This is 0, 1. And then this is 1, 1, right? So let's say this is the, actually, am I doing this? So I want row to be the first one. Yes, maybe I'll do this. 1, 0, 0, 1, and then 1, 1, right? So what we're going to do is we're going to break apart this image into 4 sequences like this. So let's say 0, 0, 0, 1, 1, 0, and 1, 1. And we're going to do something very similar. We're going to pretend like we can't take a look at this. And given the surrounding context appended to the positional embedding for each one, we're going to predict what this part is. And this lets us build basically a vision transformer in a completely unsupervised way. The interesting part of it, and I think what they did in DALL-E then, is to say, well, I have image sentence pairs, like right, so like image sentence pairs, and this could literally be like image, like basically, something you could get this like something like this from like ImageNet. And so what you do is you basically say, okay, great, I'm gonna append the sentence to the vision part. So this is the sentence, this is the image, and then do unsupervised pre-training on both. So it's a very powerful trick, but essentially this has been a recurring trend in machine learning where anything that's supervised learning is easy, anything that's not supervised learning is generally hard. And so a good way to make problems easy is to turn them into supervised learning problems. So this is exactly what this does. So again, so here, for example, like this is like I believe like sort of the main idea behind DALL-E. I'm sure there's like a lot more tricks with the encoders and such. But if we were to look at a clip, for example, it's doing something very similar where it's coming up with it's not necessarily doing like this unsupervised pre-training, but actually no, it is. So it has this text encoder, it has an image encoder. You append both of these into some intermediate representation, and then you use this intermediate representation. So here, instead of like let's say having two vectors, it turns it into this matrix. And then you can basically train on this matrix on a class. So basically, given this matrix, add a linear layer at the very end of it, make some classification, and now you can pre-train this. And now this works for arbitrary images and arbitrary classes, as opposed to only working for a fixed number of classes. This is like, absolutely like, very powerful. And the nice thing about it is that, like, well, when you're generating stuff like like a linear layer is useful if you're doing classification, but if instead you make it like, let's say that you make the last part here, for example, you can generate like sequences, you can generate images. So again, depending on how you structure your output, you can either make this a generation task, a regression task, or a classification task. So it depends on what you're trying to do. So okay, so all of this was was background, and all of this was background to understand this new paper by about multimodal neurons, artificial neural networks. And I think what they're trying to do in this paper is try to get to the bottom of like why does the clip work so well. So we already talked about like multimodal neurons and how we neurons recognize concepts and not just like specific pixels and shapes. And so they're saying like they find these multimodal neurons in clip. And so this is the okay. So they're saying we can refer you to the clip work if you're interested. Uh, And Clip's abstract visual features might be seen as a natural result of aligning vision and text, and we expect world embeddings and, language models generally to learn abstract topic features. And these features seem natural in retrospect. They're qualitatively different from neurons previously studied in vision models. They also have real-world implications. These models are vulnerable to a kind of typographic attack where adding adversarial text to images can cause them to be systematically misclassified. Okay, so let me just show you, let's see. We examined neurons found in the final convolutional layer of the vision side across 4 models. And a majority of these neurons seem to be interpretable, consist of thousands of neurons. For our preliminary analysis, the English words which most activated neuron when rastered as images. And this revealed an incredible diversity of features, a sample which we share below. So person trait neurons. Okay, so let's say show 4 neurons. All right, so this is saying like this is what like an elderly neuron looks like, a female neuron, a mustache neuron. I like that it has mustaches on everything. Bunny ears, happy, sleepy. Okay. Oh, interesting. So these neurons don't select for a single object. So for example, if you look at, they also fire for weakly associated stimuli. So for example, like because Barack Obama is married to Michelle Obama, you expect these things to be uh, like co-stimulated. Like the same sorts of neurons should be involved in recognizing these things. So they sound like here in neuroscience they call these grandmother neurons. What's a grandmother neuron? Okay, so it's just like neurons that respond to a specific stimulus. Okay. They also call them concept neurons. That's fine. Okay, so they're giving a content warning because I think a lot of the stuff may be biased. Like, let's see. So this is the what, the Hitler neuron, like German architecture of the logo. I know what this logo is. Oh, I see. So here, for example, I think what they're doing with this drop down. But here, let me zoom in a bit. Yeah. So what they're doing with the neurons here is that they're showing you like the same, like basically if you change like the nature of the thing. So that if it's indoor or if it's a logo or if it's a posture or whatever, it's gonna show you the concepts it's related to. Okay, so that's it. So they're saying we have a Donald Trump neuron. Uh, okay, what are they actually plotting here? I don't fully. Sorry, I think my package is getting delivered. Okay, first right here. Okay, so to better understand this neuron, we estimate the conditional probability of several categories of images at different activation levels using human labeling. Conditional probability of several categories of images. Oh, so games given music, black given LGBT rights, non-political generic. But what's the conditional here? There's just one thing. Is it Trump given Twitter? Is that that's so funny. Okay. Okay, let's just read this more carefully. So, which people the model develops dedicated neurons for is stochastic, but seems correlated with the person's prevalence across the dataset, and the intensity with which people respond to them. The one person we found in every clip model is Donald Trump. It strongly responds to images of him across a wide variety of settings, including effigies and caricatures and many artistic mediums, as well as more weakly activating for people he's worked closely with, like Mike Pence and Steve Bannon. It also responds to political symbols and messaging like the wall, make America great. And on the other hand, it most negatively activates the musicians like Nicki Minaj and Eminem. Okay. Okay. If we search the query X giving a speech at the microphone for various individuals on Google Images, the median activation of the person's photo and the standard deviation of the neurons over the data set. Oh, interesting. I see what they're doing. So if you know that certain neurons activate certain concepts, now you can basically count for how many such images in the data set does this line of text activate for. And this gives you like an idea. It's interesting. It's sort of like image search almost, like it's built in. Um, this is a very interesting trick actually, and I like it because like traditionally, like when you're searching the stuff, like you could like label the best examples or the worst examples, but this sort of gives a more systematic way of dealing with these things, where you have like a natural language API to think through these problems. Okay, so we have emotion neurons. Okay, evil, punish, serious, soft smile. I wonder if it's me just like overanalyzing here, but it does feel like the images have like a striking similarity to each other. Look very similar. It's almost like the same face. Like the evil one is like intense actually. The dragon and stuff like a scale, right? Incarcerated figured out like a bar pattern. It's interesting. Okay, so I think like basically given this natural language API to search through concepts, they split it up into first looking at people. It looks like Trump is by far the most triggering person and probably like in history at this point. Then with emotion neurons, and then looking uh, like you can get like you can get relevant activations in this way. Let's see here. So then we have these region neurons. Wait, how does this work exactly? Oh, this is a visualization, I think. Kind of hard to say what's going on here. I think the America one is pretty funny here with all the USA flags. I think the Holland one, sort of like this feels like Holland, right? Logos, I'm not really sure what to make of here. This is a bit hard to parse through. Denmark, okay. New Australia, interesting. Oh, interesting. And I guess like yeah, I mean, yeah, it makes sense that the model knows more about the users than interesting. This is interesting. So they bring back some of these ideas from like the original Word to Vec paper, which is like arithmetic on on images. So you can basically do a search like, okay, well, give me an image of a king, and then take the encoding of that, and then this should be like relatively close. This is very interesting. I like this because like it's like instead of just working over text, like now you have this like new modality that you can work with like in an arithmetic way. Although I do remember there were lots of criticisms about this word embedding, this like word embedding arithmetic and whether it actually generalizes. I think I saw a lot of work saying it does not, but just something to keep in mind. I'm surprised like the authors can make anything out of like looking at these images. It is saying eagle though, right? And this kind of looks like a human bird. This is really weird. Okay, I don't get the architecture. It's like bird memorabilia. This is very, very bizarre images. So this diagram visualizes a full weight matrix that takes neurons in the penultimate layer of ResNet 4 to the ImageNet class, and each gray circle represents a positive weight. And we see the model fails in ways that close but incorrect, such as its labeling of scorpion as a fish. Oh, interesting. So once you recognize certain neurons, you can see on which kinds of images they get classified and then look at the diff. This looks like it's qualitative though. Like I think these neurons would be qualitatively generated if I'm not mistaken. Yeah, I'm almost done, so don't worry about it. All right. So what Clip also does is it does zero shot classification. Okay, so they this we talked about this. So Clip has two sides, a vision side and a language side. And they meet at the end, going through some processing and then performing a dot product to create a logit if we ignore spatial structure. And the logit has this form. So we take the image. Oh yeah, I mean it's like yeah, like the image times the weight matrix times the text, divided by the norm of the image and the text. So the bilinear term has a number of interesting interpretations. So if we fix one of them, then the term WXX gives a dynamic weight vector for classifying images. Okay. If we fix a neuron on the vision side, we can search for the text that maximizes the logit. If we do this hill climbing algorithm to find what amounts of text maximally corresponding to that neuron, and we can run this on common and emotion neurons, we can see that the actual text matches up to our expectations. Oh my god, the shocked your eyes are perfectly placed. This is interesting, actually. So remember, like we're doing a form of search, right? Like given certain concept neurons, we fix the text or an image, and then we can search for the neurons that most highly activate either that text or that image. So I think they're going to be using the same idea. Please stop hating on me. False band. Okay. So emotion composition, interesting. So relaxing plus grumpy sunset is bored. Oh, that's interesting. Yeah, like the negative version of minus sunset. I see. Intimate. If you take a soft smile with a heart and you remove sickness, then you get intimate. Yeah, I don't know, but these don't make too much sense to me. So lightning, miracle, and evil plus yoga gives you powerful. This is a cool image though. Could be a metal cover. So creative is art plus painting. This sounds a bit more reasonable. The painting one is very interesting that I figured out like this is paint on a guy's face. Like, so if you take laugh and foreheads. Okay, this guy has a forehead that's showing. Doesn't look like he's laughing. Yeah, I don't know, but oh, whoa. We can serve of this broader landscape of emotion by looking at like a full vector of it. This is kind of nuts, actually. Like I can imagine, like now for something like a game, this is very interesting because, like you could basically also like have an encoding for some sort of 3D model, and then have it be either angry or disapproving or humiliated. This is insane. Like scared. Okay, I thought this was hilarious, by the way. So these are like what they're calling typographic attacks. Like the fact that you can have both images and text be part of the same, uh, like both have the representations. Like a really simple attack is you just put like a label text that, this is an iPod, and, the model gonna say like, look, it's an iPod. The interesting thing is like right after that, it says it's Granny Smith, but it's just like very confident of this prediction. So it gives you like I guess a good way of potentially defeating these attacks, even though like let's say here, oh yeah, it's saying it's a pizza, and then after that it's a laptop computer. So the model still has a pretty good idea of what the thing is. It just seems to over prioritize the text. The Stroop effect. So recognizing a mislabeled color is harder than normal. Okay. Okay, so this is here they're finally explaining what was up with those activation plots. And they explain how this stuff works here. So let's go through this, and I think we'll just do a one final skim and probably call it. So if you want to understand the behavior of a neuron, it's not enough to look at the cases where it maximally fires. We should look at the full spectrum. The cases where it is weakly fired, where it's on the border of firing, and the cases where it was strongly inhibited. So basically, plot the activation of a single neuron as a function of all the images in the data set. Right? Um, okay. And so since we have access to a validation set from the same distribution the model is trained on, we can sample the distribution of stimuli that causes a certain level of activation by iterating through the validation set until we find an image that causes the activation. Yeah, so this is basically what I was just saying. We define universally spaced buckets between the maximally and minimally inhibitory. So we plot the activation in terms of standard deviations of activation from zero. Yeah, I think they're also saying, look, these aren't Gaussian distributions because, like, I guess like some uh, so some neurons have power laws. It seems like the Trump node, for example, is a highly correlated concept with lots of stuff on the internet. Oh, and it looks like they used an image search tool to sample images in a category. I wonder what that image search tool that they used was. I imagine that maybe they used like Google search just to come up with the concepts, right? Like, as in, by that I mean, like, let's say I say dog. Like, this is a good image search for what a dog could look like. Okay, faceted feature visualization. We train a linear probe on the lower layers of the model to discriminate between those images and natural images. Okay, so I think this is where the contrastive part comes in from the facets and doors. Oh, interesting. Yeah, so it literally looks like they used like existing data sets for like, okay, these are rooms, so that's how they can. Why do we not maximize this thing instead? Okay, let's just go over. I think as a summary, we can do this. So really, I think the core idea behind all of this related work, whether it was CLIP or this multimodal neurons or DALL-E, is the fact that we can combine the main idea of BERT for both sentences and images, and create like encodings for them. And once we have encodings for each, we can combine them, and then we can use this as a pre-training step, and then use this to solve some sort of like end-level task. If you're doing this on with Clip, for example, it tends to be pretty good. It seems to outperform ImageNet at a fraction of the flops, like actually more efficient to train than ResNet, which is very surprising. but just something to keep in mind. And specifically with DALL-E as well, given that you can generally in any sort of neural network, you can change the last layer, like whether you want this to be classification or regression or a generative task. You just plop on something in the end, and you can solve different tasks. And specifically when trying to understand like why do these things work really well, this multimodal neuron works realize like recognizes that some neurons respond to concepts and that clip may be doing well because it is learning to recognize these concepts. And to specifically prove it, what they do is that they plot, like they essentially use these distribution plots. Where is it here? Where they look at the conditional distribution of an activation of a specific neuron with respect to all of the images related to that concept in a data set. So you do this plot and then you can get a pretty good idea of what's going on. So after you do this plot, uh, you can come in here and there's a bunch of other stuff you can study. One, instead of just looking at traditional word embedding arithmetic, you can also look at image embeddings to have concepts of images, right? So let's say an image of a king, and then you can do this arithmetic here. What I also thought was really interesting is this part right here, which is that in clip, there's sort of two sides, right? So when you're actually making a prediction at the very end, you have your weight, so like the weights of your model, but you also have like an embedding for your image and your embedding for your text. If you fix either one of them, what you can then do is you can find what maximally activates either the image or the text, and so this becomes like a good way to do a form of image search. Um, so yeah, I think this is and this part I don't know, like I didn't fully understand this part, but this part I actually really thought was very interesting, like the fact that we can create like a spectrum of emotions, and then maybe even combine this with some stuff in 3D modeling, and that way generate emotions for different people in a almost like an unsupervised way, right? Because this was you don't need labeled data to say like I want you to look like this, or there's probably simpler ways of doing it than doing something like this. But overall, I think these papers gave me a lot of food for thought. Definitely challenged a lot of stuff I know in machine learning. I enjoyed them. I hope you did as well. And so, like I said, the next video I'm going to be doing is going to be on distributed training in PyTorch. So if you enjoyed this, then you'll probably enjoy the other video even more. So yeah, I mean, make sure to subscribe. I hope you enjoyed this. I did. And thank you, everyone. I appreciate it. And onwards to the next video.